We are starting off discrete math with some exercises to get you thinking systematically and logically about solving problems. These problems can be solved by following some pattern, step by step, and we do this as an introduction rather than coming up with some algorithm to solve the problems. In this lecture, we will look at problems consisting of flipping a coin, the Josephus game, and building out a game tree. First, let's start off simple. We are going to be flipping one coin. How many possible outcomes are there? There will be two possible outcomes. Either the coin will land on heads, or it will land on tails. And if we have two coins, how many total outcomes will there be? There will be 4 total outcomes. We can either get both heads, both tails, or we could get heads for the first and tails for the second, or tails for the first and heads for the second. So for one coin, there are 2 outcomes. For 2 coins, there are 4 outcomes. And if we have 3 coins, how many total outcomes will there be? There will be 8 total possible outcomes. There's all heads and all tails, of course, but then we also need to have all possible combinations in between. Can you see the pattern in these examples? If we have any arbitrary number of coins n, how many outcomes will there be? There will be 2 to the n outcomes, given that we're flipping n amount of coins. Next, let's look at the Josephus game. You can read about the Josephus game in the textbook, but the general overview is that Josephus and other rebels are sitting in a circle. One by one, they go around the circle, and every nth person dies. The last person alive can escape. How do we figure out who is the last to go? And maybe who is the second to last to go, in case Josephus wants a buddy with him. So let's run through an example. Let's say we have 10 people sitting in a circle, and we remove every 4th person. So we start with the person at position 4. Goodbye, 4. Then we'll count to the next 4th person, so person 5, 6, 7, and 8, and goodbye, person 8. And we keep counting by 4s to eliminate the next person, so goodbye person 2. And we keep counting, skipping anyone who's already been eliminated, and so goodbye person 7. And we continue, goodbye person 3. Goodbye person 10. Goodbye person 9. Goodbye person 1. And the last 2 are left, so if we keep counting, person number 6 will be the 9th to go, and person number 5 will be the 10th to go. So this is where Josephus and his friend should sit. We can take a systematic approach to solving this problem by stepping through the algorithm. Now let's look at game trees. We can use a game tree to help us estimate the likelihood of an outcome set, such as if we were flipping a coin again. If we are just flipping one fair coin, there are 2 outcomes, and they are equally likely. So we can say that the probability is, for heads, 1 out of 2 outcomes, or 50%, and for tails, 1 out of 2 outcomes, or 50%. Then, if we're flipping a fair coin twice, we have 4 outcomes, and the likelihood of getting the following sequences are, for heads, heads, 1 out of 4, or 25%, heads, tails, tails, heads, and tails, tails will also all be the same. So asking the probability of getting heads, 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 tails, tails, heads, or tails, tails might be obvious, 25% each. But what if we ask a question like, what is the likelihood that the sequence will have at least 1 heads in it? Or, what is the likelihood that the sequence will have exactly 1 tails in it? Well, if the outcome has at least 1 heads in it, there are 3 total outcomes. 3 outcomes out of 4 possible, that is 75%. If we want exactly 1 tails, that is only tails heads or heads tails, so only 2 out of the 4 outcomes, or 50%. So at this point, we're not doing much in the way of actual math, but we're getting some practice in being methodical and thinking about these things as systems. Next, we will be looking at sequences of numbers and how we can come up with a function to represent that sequence. So it can take some work analyzing these numbers to figure out what is in common between them.